All right, so this is my husband and my kid, and so I'm going to teach him about the Gulf Stream and Western intensification. I've created a tutorial video kind of explaining it, so I'm going to film us watching it, and then we're going to talk about it at the end of it. But, all right, here it goes.
So one of the causes of currents is actually a frictional force from the wind. And the wind lines up in these beautiful patterns of latitudinal lines because of the Earth's rotation. The Earth rotates in the counterclockwise direction. So wind along the equator at the 0-degree latitude line, or what's called the trade winds, gets pushed from east to west. And what that does is that causes a frictional force that pushes water this way. And as that water is getting pushed this way, once it hits landfall, it gets pushed up here, and then it's going to congregate into what's known as the western boundary intensification. There are 5 currents that make up this western boundary intensification. There's the Kuroshio current, the East Australian current, or the EAC. If you're thinking of Finding Nemo, I always think of Finding Nemo when I hear that one. There's the Gulf Stream, there's the Brazil current, and there's the Agulhas current. And each of the corresponding currents line up on their continental east coast sides because they hit that landfall. But the reason why the water intensifies there is not just because the wind pushes it, but it's also due to the Coriolis effect. So if we look at the Navier-Stokes equation, specifically the x-driven momentum for the Navier-Stokes equation. So as this water is being pushed from east to west, we can consider this directly like a Cartesian coordinate. This is the x direction, and then north to south would be considered the y direction. When we look at the Navier-Stokes equation, so the x-driven momentum, the water is being moved from east to west in the x direction. There's this term called the acceleration due to the Coriolis parameter. And it is perpendicular. So this v stands for the fact that it's going to go in the y direction. So what this term means is that because the Earth rotates, because that's where the Coriolis parameter comes from, because the Earth rotates, it's going to be pushed or pulled in the perpendicular direction to its motion. So that's where we get the circular patterns. And it's the relationship for this perpendicular push or pull is actually it's a sine relationship. So at the equator, where the latitude is 0 degrees, because this angle right here is for the latitude, the sine of 0 degrees is 0. So we actually have no Coriolis effect really happening at the equator. So as the water moves along the equator, it's going to pretty much go in a straight path trajectory until it hits this eastern coastal line. And the landmass will physically cause it to divert up. And then the Coriolis parameter, as the water gets further north, this angle here, this phi angle here, is going to increase. And as this increases, the Coriolis parameter is going to have more of an effect, more of a force, curling that water, so to speak, turning it, pushing it perpendicular to its motion, which is what causes this curl and concentration here, and where we get these strong western boundary currents. And the further north we get, the stronger that Coriolis parameter is. If we're comparing latitudes from like 0 degrees, 30 degrees, and 60 degrees, just kind of giving general examples, little samples of it. If we were to look at the percentage of the Coriolis force that would have an effect on, at 0 degrees, we have like it essentially approaches 0. There's no force effect from the Coriolis parameter. But at 30 degrees, you get like 50% of the force. At 60 degrees, you get 86.6%. And then at 90 degrees, you get the full 100%. Because of this variance, which you can also call Coriolis deflection, it causes these strong currents on the eastern fronts, right, the west boundary currents, to congregate. And then what it actually does is it causes on the eastbound side, so on the west coast, not to get them confused or mixed up, causes weaker currents and more diluted water. And so what Stommel did is he conducted an experiment to prove this using just a simple rectangular pool model. And he actually used the rectangular pool model because of where all the 5 western boundary currents were located. He kind of ruled out that topography didn't have a big role to play because they were all in various different parts of the earth. And so he set this up, and he tested 3 different three different experiments with this. One where we had no Coriolis parameter, one where we had a constant Coriolis parameter, and one where we had the Coriolis parameter that mimics Earth. In the case where we had no Coriolis parameter, what happened was, so he had winds that kind of emulated the northeast trade winds, and would blow across the south part of this, you could think of it as a rectangular swimming pool. But so he had these trade winds that blew this direction across the south. And he also had these winds blowing across the north part of, or the top part of the tank, that mimicked the westerly winds that you see kind of in the northern hemisphere, that little chunk of ocean in the northern hemisphere. What he found was that you had a uniform circular motion, and that much like when you stir a spoon in a cup, the water towards the center had a dip. Now, when he added a constant Coriolis parameter, so one that didn't change with latitude based on where you are in the globe, he added the same winds, right? The same trade winds at the bottom, the westerlies at the top. He found the similar circular motion, but in this case, there was that Coriolis force that was pushing water towards the center of the pool, and created a rise in the water. And then finally, when he varied the Coriolis force as a function of the latitude, he found that water congregated on the western boundary, just like the western boundary conditions and all of our strong currents. So all western boundary currents are strong because of the direction of the winds, the variation of the Coriolis parameter as a function of latitude, and Stommel proved this with a very simple experiment.
Okay. So you were riveted the whole time, yes?
Oh, yes.
What did you learn?
Oh, I learned that, oh dear, sorry.
Come here, Buggy.
I learned that, because of the rotation of the Earth,
Okay, we can maybe edit
that,
this one.
winds go a certain direction, and because the winds go that direction, that's what makes the water flow that direction, and it goes up because it hits the land and has nowhere else to go.